Thank you, and thank you to the organizers for giving me the opportunity to speak today. So I'll be talking about a simplicial pooling layer, which is interested in if you're using neural networks and your data comes in the form of a simplicial complex. There's lots of different simplicial neural networks that have been defined, but we're working on specifically the way you can coarse in a simplicial complex for use in your neural network. So in general, the type of input data you're working with should determine the type of neural network you're using. Of course, if your data comes in the form of some sort of grid with a nice regular structure, neural networks like convolutional neural networks are naturally suited for this because they can leverage the natural Euclidean structure that is there. But if instead your data comes in the form of a graph where there's less regular structure, you'll use a graph neural network or a GNN. And this allows you further flexibility. So instead of having this nice regular grid-like structure, you'll instead have to use something like the adjacency matrix to keep track of where the local neighborhoods are on your data. But what we're interested in is a further generalization of this. So in the case of data coming in the form of a simplicial complex, where you also have these higher order interactions that you'd like to model in your data, perhaps instead of just features on vertices and edges, you also have some sort of features on higher dimensional simplices, like 2 simplices or 3 simplices. And the way that this is typically dealt with is using a simplicial neural network, where you have to use this additional structure and facilitate message passing between the simplices of higher dimension as opposed to just on the vertices and the edges. Okay, so if you are familiar with graph neural networks at all, you also may be familiar with pooling layers on graphs. There's a lot of different ways that people do this. There's clustering-based methods. That's sort of what I'll focus on today, but basically coming up with a way to break down your graph into clusters, and then using those clusters, there's a natural way to generate a simplified graph from this. Each of the clusters becomes a new vertex in your graph, and depending on connections between clusters, you can add edges back in. But you can see how this is further complicated as soon as you add in higher dimensional simplices, because you can use the vertices to define your graph in the same way, but what if you'd still like to retain some higher order information and not just reduce all the way down to a graph? So this is the main problem we're aiming to tackle. We are trying to define a pooling layer for data that has signals on higher order structures, so beyond just vertices and edges. And these pooling layers can be interleaved between standard neural network layers, of course, simplicial neural networks specifically. Primarily, this serves to reduce the size of the simplicial complex, which of course reduces the computational complexity. This also has a couple of purposes that are the same as for graph pooling layers, which is to limit overfitting in your model. So the neural network model tends to overfit, and pooling layers in graph neural networks can help mitigate that. They also help to speed up message passing between simplices that happen to be far apart on your complex. So we'll see that in an example later on. But the additional challenge we have with simplicial complexes that we don't have to deal with graphs is that removing a simplex of one dimension affects the existence or possible existence of simplices in both dimension directions. Okay, so I'll start with a brief primer on some important information for graph neural networks that will help you understand why this problem can be a little bit more difficult. So standard graph level GNN layer looks like this. Your input is the features on vertices or edges, which is given by this matrix X here at layer L. You have the adjacency matrix here, which represents the structural information for your data, and it tells you where the local neighborhoods are. You have a nonlinearity here, maybe a ReLU, nonlinear activation function. And essentially what the graph neural network layer is doing is it's aggregating information of nearby vertices. So for a given vertex here, V in pink, at layer 0, it only knows information about and features about itself. But after one layer, V is able to accumulate information from its one-hop neighbors. After 2 layers in your graph neural network, V is now able to accumulate information and aggregate information from 2 hops away. And then at the end of your neural network, perhaps you use this information for just vertex level tasks, if you're doing link prediction or something like that, or maybe you want to use all of these embeddings and use a readout function And then you end up with an embedding for your entire graph, and that gives you a lower dimensional representation that you can use to do something like graph classification. But the main thing here is that the primary structural tool we're using is the adjacency matrix to tell us what the structural information of the graph is. So the way that pooling on graphs work, this is an example, a different diff pool, which is a way to generate hierarchical clustering of these graphs as you pass through a neural network. So this is a really commonly used pooling layer in graphs. And this works by combining two neural networks. It's an embedding GNN and a pooling GNN. The embedding GNN gives us a way to learn vertex embeddings. So basically it's taking the adjacency matrix, and it's taking the features on vertices and a learnable weight matrix here, and you're coming up with embeddings for each of your vertices. The pooling GNN has the same set of inputs, but the addition of a softmax function at the end, which gives us an output, which actually is the cluster assignments for each of the vertices. So each of the vertices in your graph now have a single cluster assignment. And this is really nice because now using just these two matrices, Z and S, we can do some simple matrix multiplication, and it gives us a pooled version of our graph. So by multiplying the cluster assignment matrix against either side of the adjacency matrix, we get a coarsened version of an adjacency matrix, and that represents the pooled version of our graph. And similarly, we multiply the cluster assignment matrix against the output from the embedding GNN, and this gives us an output which are our new features on meta vertices in our pooled graph. So this is work that has been done. This is how graph pooling using this specific method works. But as you all are familiar, once you think about adjacency in terms of simplicial complexes, we have more base relations to keep track of. So we can think about adjacency on a simplicial complex in terms of 4 different types of neighbors. Obviously, the boundary adjacent neighbors are just represented by the boundary matrix. And for this example, edge sigma here, it has 2 boundary vertices. Or if you want to consider simplices of 1 dimension higher, you can look at the co-boundary adjacent neighbors, which are all of the simplices of 1 dimension higher, such that your simplex of interest is a face of that. In this example, is given by this 2 simplex here in green. But you can also consider the set of neighbors that have the same dimension. So the lower adjacent neighbors are given by actually this combination of 2 boundary matrices. In this example, the lower adjacent neighbors, you can see if you're starting with the edge sigma, are all of the simplices that you can get to by crossing a simplex of 1 dimension lower. So they're shown in pink here. You can cross this vertex, get over here, this vertex, get over here, and so on. And so this lower adjacent definition is actually the direct generalization of graph adjacency. So if you think of 2 vertices on a graph, we know they're adjacent if there's an edge connecting them. That's upper adjacent. But for upper adjacent, if there's 2 vertices on the graph, we know that they're adjacent because they have a higher dimensional simplex that connects them. So that you can generalize that to higher dimensions with this upper adjacent definition given by the combination of these 2 boundary matrices. And one thing to note about the lower adjacent and upper adjacent definitions here is these are actually the down-up and the up-down combinatorial Laplacian operators on the graph. So when you sum them together, these 2 terms, these boundary matrices plus these boundary matrices, it gives you the pth dimensional Hodge Laplacian. And that's going to be our primary tool to facilitate message passing on simplicial complexes. Whereas in the graph case, you can use the adjacency matrix and the graph Laplacian. And it's also important to note that if you take your dimension P to be 0 here, your upper adjacent term here is B1 transpose, which is in fact the graph Laplacian. Okay. So similar to the standard graph neural network layer, this is an example of a simplicial neural network layer that uses these combinations of boundary matrices of different dimensions to facilitate message passing between all of the simplices of different dimensions. So again, the X matrices represent features on simplices of dimension P -1, P +1. This is the P-dimensional Hodge-Lagrangian, which you get by summing up the two different lower adjacency and upper adjacency operators. And then you can facilitate message passing in this way by multiplying and getting your learnable weight matrices for each of these terms. And similar to the graph case now, if you look at the edge E, you can see as you traverse through the subsequent layers of this network, how the edge E can gather information from simplices that are further and further apart on the complex. Okay, so now I'll get to the particular problem that we're interested in, which is being able to define a pooling layer for these cases. So our goal is to generate similar to DiffPool on graphs, is to generate a hierarchical representation of these simplicial complexes that we can get using just a learned vertex pooling of the underlying graph. And then we're able to extend these clusters on just the vertex set to all of the higher dimensional simplices in a deterministic way. So this really reduces down to passing in a partition of the vertex set, and then you can tell me what the coarsened simplicial complex should be. And so I'll discuss this first through the topological formulation of the way we think about this, and then in practice, this is obviously a series of matrix multiplications, how we do this, and I'll explain how we get to that point as well. So on a simplex, we define the local neighborhood of a simplex using the star definition. So we're starting with a partition of our vertex set in two clusters, which are given by each of these different colors on our simplicial complex. Each vertex is assigned to at least one cluster, but it can be assigned to more than one, as you can see in this vertex example right here. And so using the star of a simplex now, we can extend these clusters by taking the union of the star of each vertex in our cluster. And now each of our entire simplicial complex should be covered by these sets, because if we take the star of each vertex within a given cluster, we've extended out these clusters in a way that the entire simplicial complex will be covered as long as each vertex was assigned to at least one cluster. So you can see an example of this on the bottom here. Each of the vertices started with their initial assignment to a cluster. We took the star of each of the vertices and the union within each cluster of that star set. And then we have an open cover of our simplicial complex, and we can use the NervePool to just generate a new complex from this. So each of the individual clusters becomes a vertex in our NervePool construction. Whenever we have a two-way intersection of clusters, which are shown by colors here, you get an edge. Anytime there is a three-way intersection, you'd get a two simplex and so on. Okay, so as an overview of how this works, I hand you a soft partition of the vertex set, which is shown by the colors on the leftmost picture here. We extend that cover to cover the entire simplicial complex by using the star of each simplex and taking unions within clusters. And then we can just use the NervePool to define a pooled simplicial complex, and this is defined by the NervePool construction. Okay, so what does this look like in practice? The matrix implementation of this again starts with just the cluster assignments of vertices, which is given by this matrix S sub 0. And this, the size of this matrix is the original number of vertices in our complex by the number of pooled vertices in our complex, which is the number of clusters. So this is represented by this section in our block matrix over here. And the goal here is to fill out this entire block matrix such that we have a map from all of the simplices in our original simplicial complex to all of the simplices in our pooled simplicial complex. However, this is a little complicated because we don't know the size of this block matrix ahead of time. And so we do this by filling out this large block matrix, all of the entries in the lower triangular part of the block matrix, and we don't care about all of the entries up here. So the first way we do this is filling out the first block column. And you do this by considering For each row in these entries, these represent simplices in our original complex. So we know the vertices that make up each simplex, and we can go back up to our first block and check to see which clusters they were a part of. And you can fill in ones or zeros depending on their cluster assignments. Then we fill out information moving across the matrix. And this update is a series of entry-wise products of columns from this original block column here. And this is actually where it's a little bit more interesting because we don't know the actual number of pooled simplices that we'll have in our new complex. So if we get columns that are all zeros, we know we can disregard, but it is a computational cost because we have to check all possible pairs for the one simplices, all triplets for the two simplices, and so on. Okay, so once we have our large block matrix filled out, what we're really interested in is just the blocks on the diagonal. And so these tell us maps between the original vertices to the pooled vertices, the original edges to the pooled edges, and so on as we move across the diagonal. And what we do here is now, instead of with graph pooling, where you can use the vertex cluster assignment multiplied directly against the adjacency matrix, we now want to multiply these different S's of different dimension against boundary matrices. We do this on both sides, but it requires that we have different dimensions. So we need the S matrix, the cluster assignment matrix of a dimension lower and the current dimension, because boundary matrices are not the same size. They're not symmetric. And so we end up with this new pooled boundary matrix. And if you'd like to see what the simplicial complex that comes out from these boundary matrices at different dimensions are, you can just multiply them together in the same way to get a new adjacency matrix that represents your simplicial complex. You could also do this using the lower adjacent definition as well, but those two should be compatible with each other because they're based on the same boundary matrices. Okay, so we've been able to show that the topological formulation that we described in terms of sets is compatible with this matrix implementation that we've done. So if you follow this image down on the left-hand side, this is the more set theoretic interpretation, starting with the soft partition of the vertices, extending your clusters, and then using the nerve to get this simplicial complex. You can do the same thing. This is an example of the large S matrix, which tells us all the cluster assignments where the shaded in values are just non-zero. And then pulling out just the block diagonals here, multiplying them against the corresponding boundary matrix that they belong to, gives you these, in this example, these two output boundary matrices that have non-zero values in a way such that the output adjacency matrix you get is compatible with the simplicial complex. So it gives us the same result, but doing this via matrices. Time, so I will do this as well. You might be curious about what the learned piece of this is, because I said that you're handed a soft partition of the vertex set. And that's part of what's interesting about this is that it's actually our simplicial pooling method is actually agnostic to the choice of the vertex partition you're using. So you can use any type of graph pooling method you like, and this should be compatible that you can then extend it to the simplicial complex as well. So there's this nice formula that Bertola showed in 2021. We're breaking up the idea of graph pooling into these three steps where you're selecting, you're reducing, and then you're reconnecting. So you're breaking up your graph into clusters, then you're reducing, so you're getting reduced embeddings for each of your meta vertices, and then you're connecting your graph back up to determine which edges should be paired or which vertices should be paired via edges. And if you can think about our framework in the same way as well, we're using any choice of trainable graph pooling method. The select step is really just learned from the one skeleton of your simplicial complex. And then there's slight adjustments to the reduce step because you have to take into account the higher dimensional simplices as well. And so the diff pool for graphs is broken into the select, reduce, connect steps here. You get your cluster assignment matrix using a graph neural network, which is shown by this. you are able to reduce that by multiplying your cluster assignment matrix against the embedding GNN output. And then you connect it based on the multiplication of your vertex cluster assignment to the adjacency matrix. But in our case, if you'd like to do this for simplicial complexes, you have the same select step. You're still doing the vertex pooling in the same way. The reduce step has additional information needed because now you have to use all the extra boundary matrices, and you have to use a simplicial neural network instead of a standard graph neural network because you have to keep track of the higher dimensional simplices as well. And then this, you have to do the extension to fill out the entire S matrix, and then connecting them is using the boundary matrices instead of the adjacency matrices. So this is just a sort of schematic that explains that also in a different way. If you're to use diff pool specifically to come up with your vertex clustering, how you'd extend that then to generate your pooled simplicial complex at the end. But I will skip over that. Overall, we've been able to show that this matrix implementation is compatible with the topological formulation up to reweighting of the simplices. And this is a pooling layer, which is permutation invariant. So if you permute the simplices, you should end up with the same output simplicial complex, which is important in simplicial neural networks. Basically, this collapsing in simplex information only flows down in dimension. And it's interesting because the collapsing of collections of vertices is entirely determined by how you choose to cluster your vertices. And so you can get weird behavior based on how you're training your data, because you could have simplices that are assigned to or vertices that are assigned to the same cluster that are very far apart on your simplicial complex. So it's not doing anything like retaining homology or things like that, but you could potentially do interesting things with adding topological loss terms if you'd like to do something that's task specific to retain something like homology or some other topological measure of your simplicial complex. I will leave it at that, and thank you all for your attention. I'm happy to take any questions.
Thank you very much. I see a little window with the audience, so are there questions for Sarah? Maybe Tamal can help me, and because I don't see if somebody raises their hand.
Okay, so there is two hands going up.
Okay.
Okay, so
whoever showed first, yes.
So recently there has been two libraries. One is TopoNetX and TopoModelX. I'm just mentioning because you may get immense benefit from that. Like there you can do this simplicial manipulation, simplicial message passing, and then you can get those adjacency matrix really easily. So
Yeah.
just to it may benefit you. That's
Thank
it.
you.
There is another question. Yes.
Yeah.
I was a bit concerned, like, I mean, like, when you do the pooling, there's no, like, you guarantee that you can generalize the, I don't know, I use like the professional world, I can, yeah, I mean, like, if you don't do that, then you know what's on the way.
Well, it's very task specific. I mean, it would depend on what you're using it for.
I think the baseline usually you have to preserve from.
Yeah, for graph pooling, that's often the goal, is to preserve the spectrum of the graph population.
Is there any question online?
No.
You can ask the question. So I wonder, I wonder what the relation to mapper, because it appears very similar, right? I wonder whether you could define a function on the point such that the mapper graph would be the same graph, or not the mapper graph, the mapper complex would be the same as yours.
Yeah, there's also I know Christian Bodner has a paper it's a version of simplicial complex pooling where they are using mapper and the output is always a graph. So there is a version of it. You but your output is always a graph. In this case, we're retaining the definition of a simplicial complex as well, if that's the way that the vertex partition is learned.
There is another question. I see now in the back.
Possible to implement the TDA-Jyamiti without actually okay, sorry, using weight, right? There's a learnable.
Right.
Yeah.
Well, it's normalized. So you start with just the vertex assignments. That's normalized, and then you normalize it all of the, once you fill out the entire matrix, then you normalize by row. So that it's not
Yeah, I'm just thinking like that expands the computation.
it does, yeah.
What do you usually take based on the enforcement and how many factors?
I think it would depend on the application. It would highly depend on the application. Yeah. I will say that, yeah, obviously filling out this entire matrix could be computationally expensive, but the use of simplicial neural networks in general, I think, is computationally expensive, and it is prohibitive to do this type of analysis using simplicial complexes as your input data, and then using the simplicial neural networks, because all of the message passing is very expensive. So the addition of a pooling layer, which is able to then reduce the size of your simplicial complex as you're passing through the network, is valuable if you'd like to use a simplicial neural network.
Price to pay for the
It's
pooling.
bad,
Actually,
but less
it's
bad.
bad, but it's not as bad as paying the full price.
Right.
Okay.
Michael, I don't see any other hands.
Okay. Yeah, so let's thank Sarah again.